Welcome everyone to this week's data science seminar. I'm David Bader and I direct the New Jersey Institute of Technology's Institute for Data Science. I'm very pleased to have a speaker here today, Yanchi Liu from NEC Labs America. Dr. Yanchi Liu is a research staff member in the Department of Data Science and System Security at NEC Labs America. He has broad interests in data science, artificial intelligence, natural language processing, and their applications to solve real problems. His current research develops efficient and effective techniques to address various challenges in business analytics, complex systems, and urban computing, and to ultimately assist intelligence decision making. He's the author of over 70 technical papers and a recipient of the Baidu Research Fellowship. Dr. Liu is speaking today on domain-oriented natural language processing. If you have questions in the talk, please use the chat and moderate those at the end of the talk. Dr. Liu?
Thanks everyone for joining this talk. So today I'm going to talk about the domain-oriented natural language processing. So my name is Yanchi Liu from NEC Labs America. First, as we all know that other than the structured data, nowadays unstructured data are quite increasing processed nowadays. As for 2020, there are more than 80% of the data are actually unstructured. For the unstructured data, there are various types like text, video, audio, those kind of things. Different types, but among all of them, text data are actually the very important part. So that cause the natural language processing techniques are quite popular and quite important nowadays. So as we say, natural language processing, that involves some kind of task, like they can help us to communicate the computer and the human, right? So it will help bridge the gap between computers and the human, to make the computers to understand the human language, so that they can help process the text data or documents generated, and can scale up the ability to process different tasks. Some of the typical tasks in NLP that includes like question answering, information extraction, and also translation and sentiment analysis. So all these different tasks are actually quite normal in our everyday life. So like for translation, right? So possibly every day I need the translation tools to help me translate English to other kind of language like Japanese, Chinese, those different applications. So NLP nowadays is quite important and can be applied to many useful tasks. But for this topic, I'm going to focus on the domain-oriented NLP. So why we need to focus on specific domains? So that's because for each domain, actually they have their own language, right? For example, in financial, in bio, those different domains. So they have their own terms. They have their own phrases. If you cannot understand those terms, possibly you don't understand what they are talking about, right? So it's also very important for us to understand the specific domain language to help us to retrieve the knowledge for those different domains. And also it's very important to retrieve those domain knowledge to make different decisions, right? As you can understand those domain language, you can make the right decision according to the knowledge you can get, right? So that those computers or algorithms can help us to scale up the ability for human to process those large amount of data. So those different, so that's why, and also as we in the industry lab, so we have those different kind of data. So have different applications from different domains. So that's why in the NEC Labs America, we initiate this research direction focus on the domain-oriented NLP. And also here is a pipeline kind of for either of the domain-oriented NLP and as well as the general NLP. We normally follow this kind of a pipeline, right? So from the pre-processing, in the beginning, we have the raw text. So we need some pre-processing, like tokenization. And the next level, especially the augmentation for the specific domains, we have different kind of data to help us to provide the knowledge other than text, right? For example, the image, the graph. So some industry, they have their knowledge graph. They can provide quite direct information to the knowledge we need. So to augment those different types of data, that can help us to provide the domain knowledge. And the next level is the representation or language modeling. So it's also one quite popular way to represent those text, like word, phrase, like sentences into latent space with embedding vector. So that can help us to extract some kind of meaning of the semantic meaning of the text, right? If they have similar meaning for those two words, we may have a embedding vectors that can be located near to each other, so that can help us to extract the semantic meanings and then help us to understand the language, right? And then we have various NLP specific tasks, like the classification, information extraction, similarity matching, summarization, or language generation. So we also have other types of tasks here. Here we just some typical tasks, and at the top layer we need to apply those different tasks into the real applications, right, to solve our real problems. So here we also have in NEC Labs we have many different applications, like from business, finance, security, logs from the complex systems, and also healthcare. So here is a pipeline that formats all work. And in this talk here, so I'm going to introduce one piece of work that focus on the representation, that is language modeling. And after the introduction of that work, I will also introduce some of the efforts we have made on the different applications. So next, I'm going to first introduce one work that's the domain-oriented language modeling. So this one paper published on this year's KDD. So for language modeling, as I introduced, so that's on the representation layer. So it's trying to map those texts into a latent vector. Right? So it's quite important. Actually, it's a foundation for various NLP tasks. So for those different tasks, we all need some kind of embedding vectors of the text or the language, and then we can utilize different machine learning models to finish, to help us to solve the tasks or problems. So for the domain language modeling, so actually we have various language models like the most recent, like the BERT or the GPT-3, those different language models. They work quite well on general information processing, but they are not well adapted to kind of specific domains, since they either the state-of-art method just either further pre-train the model into specific domain corpus, right? But they just follow the original method, just to do some further pre-train. But in this way, they do not consider some kind of specific domain knowledge to be integrated into the model to help us to retrieve the knowledge. For example, we have different kind of phrases or terms in different domains, right? But the current model, they do not take this part into consideration. So like the most popular used mask language model in BERT, they just mask the words, but they do not mask the phrases. So in this way, actually the phrases are quite important in domain to help us to understand the languages. So in this way, they cannot fully understand the phrases. So that will cause some problem when we use those language models into different tasks. So in the right side is one example, right? So one example for the aspect extraction in the review dataset from Amazon. So we can see that the extracted aspects that marked in color, actually they are usually phrases, right? Since one word, they might not able to describe what we want. So usually those aspects are in phrases, but the existing methods may not well adapted to help us to extract the phrases. And we also did some initial experiments to reconstruct the words or phrases, right? So we can see that when we want to reconstruct or fill in the missing like 2-word phrase or 3-word phrase, then the performance or the accuracy is going to drop very dramatically. So the phrase level domain knowledge is one kind of knowledge we want to integrate. And the other thing is that some kind of entity level domain knowledge is also missing. Since for here we use one example from the e-commerce area. So we know that in many domains we have this kind of graph that can have some kind of connection between the entities or other things in the specific domain. So actually from this graph, they can provide very direct look into the domain knowledge. For example, if we have 2 products, they are co-bought or co-viewed by our user, we know that they might have some kind of relationship, right? For example, the monitor and the display. So we know those 2 products, they have some kind of relationship, but if we do not consider the graph, then we don't know those kind of relationship. They are quite related. So if we only try to find those relationships from the text based on the frequency, so that's going to be quite hard. And if we can utilize those graphs to help us to find those information, So that could be quite useful, right? But those graph information, they can only provide some very weak singulars. So if, for example, if two products, they have some kind of relationship, but it's quite noisy. We don't know what kind of relationship and what exactly the words are related to each other. So here we need to further clear this gap, this gap here to filter out those noisy information and find the clear connection between the words or the phrases. So here we provide a two-stage pre-training approach to help us to get the domain-oriented language model. So in the first stage, we use adaptive hybrid mask model to help us to obtain the phrase knowledge. And in the second stage after that, we use a cross-entity alignment to help us to gain the entity knowledge based on the entity association graph we generated, so that we can learn both those phrase and the entity knowledge, and then we apply the trained model into different downstream tasks, and we those 4 tasks we done those different experiments to validate our model. So next, I'm going to introduce those 2 stages one by one. So before getting to that, I first want to introduce the mask language model. As we all know that in BERT, those very popular language models, they use the mask language model as one of the tasks to help to train the model, right? So given one sentence, we remove some words in that sentence, and then use the context information to help us to fill in the missing words. So in this way, we can train the missing words based on the context, so that to build some kind of connection between those words and the context information, right? So in this way, we can get some kind of contextualized embedding vectors of the word, so that we can get the semantic meaning of that word. And but in this way, they in the previous models, they only mask the word, so that they only want they can only train based on the missing word to fill in the missing words. So here we think the phrase is also one important part to help us to understand the language, right? So in addition to the word learning mode, we add another mode that is phrase learning mode, as we can see from the picture here. So the above part, we still stick to the word learning mode to mask the words to help us to learn the word embedding. And also in the below part, we use the phrase learning mode to mask the phrases, and then we want to reconstruct or fill in the missing phrases, so that in this way we can also build the connection between the phrase and the context. But one contribution here is that we can use those 2 modes to be adaptively switched, so that we do not train one mode after another, right? So that's one way, but that can cause more resource, like more data to train to achieve the same performance. So that's so in this way we can save some time, or with less data we can achieve the same performance. Right. So the first one is the word learning mode. So it's the same as the model used in BERT or other language models. So like here, we mask one word in the sentence, and then we want to use the training data to help us to fill in the same word, right? So and the second is the phrase learning mode, so that we first use the domain corpus. We use a tool to help us to first extract some domain phrases to form an external domain phrase pool. So we mask those phrases inside this pool, so that can help us to more directly get into the domain phrases. Right? So we do not just mask random phrases, but we first use some pre-processed domain phrase pool to help us to get directly into the phrase we want. And then we mask those phrases that can help us to get more directly into the knowledge we want. So similar here, we mask the phrase, and then we predict the words in the phrase. And also we add one regularization here is that we want to predict all the words correctly. Right? If we're missing any of the words in the phrase, we're going to penalize the output, so that we can that can help us to learn this model. So, right, for example, here is one example. So we mask the phrase like the local pub. As long as we can predict the those two words correctly, we can minimize the loss here. Right? So in this way, we can learn the phrase knowledge. And here we use another mechanism, that's the adaptive learning. So as I introduced, we do not learn one mode by another. So although that's also one way to learn, but may not achieve the optimized output. So here we use adaptive learning that's based on the loss of those two different modes. So so in each step, we have the loss of those two modes, right? And then we compare the loss increase of those two modes. So for example, if the word mode can only reduce the loss by maybe 1, and then the phrase mode can reduce the loss by 10. So we can see we can learn more from the phrase mode, right? So in the next step, we might still need to train on the phrase mode. So that's the idea of the adaptive learning, so that we can switch for each step. We can switch between the word learning mode and the phrase learning mode to help to maximize the efficiency of the output of the training output. Right. So that's for the first stage, and then for the next stage, we want to learn the entity knowledge. So basically, that we have the in this work, we have the entity graph that connects the products. Actually, we say here that one entity is one product, and we have the product title, right, as here. So like the Nike basketball shoes. So we have different words inside, and we have the graph, a relationship connected to another product. That's the Adidas sneakers. So that we know there are some kind of a relationship between those two products, but we don't know whether which words are related to each other, right? Since the Nike may be more related to Adidas, since they're all brands. So we want to find the alignments between the words inside the product titles, so that we can learn the connection more how to say, more direct connection between the words, so that can help us to further refine the language model. And here we utilize a method that's optimal transport. So this one is it tried to solve the problem of transforming one probability distribution into another. Right. Since here we have the data, maybe in this graph I can show more clearly. So, for example, we have the embeddings that's generated from the language model we trained, and then we have the output. We have the embedding vector for each word inside the entity or the product, right? We have the vector of each word. So X is a matrix of the entity X, and the same. We have another matrix for the entity Y, so that we want to align the words in X to the to maybe one vector in Y, so that we want to minimize the transport. Right? We want to transfer from one to another, and we want to minimize the cost of the transformation, so that in this way we can align the I in X to J in Y, so that we can align those two words together. And for the others, maybe they are not so aligned. Then we have other we can have other kind of cost, so we can neglect them, but more focus on the aligned word pairs. So actually the optimal transport help us to solve this problem, to help us to align the words into sentences or into product titles to each other. So in this way, we can align the maybe Nike to Adidas, and then we can also align the shoes into the sneakers, since they are based on the semantic meaning, they are more related to each other, right? So the optimal transport help us to solve this problem, and based on the transport, we have we want to minimize the loss, right? And then based on the loss, we can further help us to refine the language model. So those are the two different stages. One is focused on the phrase, and the other one is focused on the entities. So in this way, we can learn the domain knowledge from those two. And next is the experiments. Actually, we have done some experiments based on the e-commerce domain. That's some text data are collected from Amazon, and also we have some user behaviors, like which products the users buy together or view together. From those user behaviors, we form the entity association graph to connect those products. So that's going to be another input, right? And as I introduced before, we also form a domain phrase pool, use auto phrase tool So this tool is independent to the domain. So we can extract the phrases from the domain corpus and then use that tool to help us to mask the phrases. We have 4 different tasks to validate our model, as like a review question answering, the review aspect extraction, the sentiment classification, and the product title categorization. So normally after we get the language model, we need to apply to different tasks. So in this step, we further fine-tune the language model based on the different tasks. Right? Okay. So here I just want to show our domain phrase pool actually is quite different from just extract the long phrases. So in this way, our domain phrase pool actually can be more effective. That also is shown in the experiment results. So we have different baselines, like we compare our baseline to the external baseline, like the BERT or Steinbert, Norbert, Albert, those different kind of external baselines. We like the PT here is like we further post-train the BERT model on the domain corpus, and the NP here is that we mask the long phrases of the BERT model to further train that. And we also have different internal baselines that's based on the different components, right? Like we only use the phrase mask. We only use the cross-entity alignment. So based on different components, and then we have different metrics to help us to evaluate. So here shows the results. As we can see from the table here, so we have from those 4 different tasks, our method actually can improve the performance quite well. I think from 10% to maybe 5% depends on those different tasks. So that we can see we can conclude that actually the phrase and as well as the entity alignments can help us to gain the domain knowledge quite well. And since they provide they other than the text, they actually can provide more direct domain knowledge to us, and then that can help us to learn more efficiently. Right. And here is one example on the aspect extraction. Right. So as we showed before, actually the aspect extraction is quite phrase intensive. So most of the extracted aspects are phrases, right? Like here we have the review of one product, and the baseline are marked in color, right? We can see the size of screen. That's actually the user focus on. But if we just use both, they might neglect the size, just the screen and the resolution, so that's the same. So, but with our model, we can extract the correct phrase. That's the size of the screen, not just screen, right? And also here, we can focus more on the phrases that actually can provide more meaning to us, right? So not just the one word. So sometimes the one word cannot express the correct meaning. And here is one case study to show the alignments between the entities. Right? So here here is one product on the left, and on the bottom, so that's another product. But we have different words in the product title, and we can see it here. After the alignment, we can more connect the related words like slicer to chopper, right? And dicer to slicer. We can connect those more related words together, but neglect those unrelated word pairs. And similar here, we have another product. So that's the display docking station to the monitor. We can connect the display to the monitor. We can align them together, and some other unrelated words we can assign less weight to them, and they are not so important in our learning process, right? So that can help us more focus on the related word pairs to help us to gain the knowledge. Okay, so that's something related to all recent research efforts on the domain-oriented language modeling. And next, so that's some domain applications I introduced. That's something involved in our labs. So basically, all the research actually generated or oriented from those real applications we encountered. For example, the previous domain oriented language modeling, actually that's some efforts we want to solve the business matching problem. So business matching is so they want to identify and connect companies that have common business interests and the services, technology or business experiences. So we have the needs from different companies. They post it. So like one company say, we are looking for some contractors for resident security services in some kind of area, like NYC area. So that's some text posted by different companies we have, and we want to connect them together based on the needs that posted. So first we need to extract those different information from the text, right? So what they are looking for, and what kind of services they are looking for, and in what kind of location. So we first want to extract those different information to help us to match. And the next step is that we want to measure the similarities between those entities we extracted. So actually, we have another research ongoing that's more focused on the similarity of those products, since maybe we think it's quite a simple problem to measure the similarity between different products, but actually it's not that easy, since for example, the products have different categories, and they have a hierarchy, those structure, right, for the products. So we encounter many cases that one company wants some kind of IT services, but they don't know what exactly the IT services they want. But other companies may say we provide AI technology or machine learning technology or system or log analysis, right? So sometimes we need to measure the similarity between different hierarchies. So that's actually need us to consider different kinds of information insights to make that able to be compiled. And another nice that we also want utilize NLP for the log analysis. So logs actually are quite important to help us to detect the failures or anomalies in the systems. But in the other point, log actually is also written by the developers. It's also one other kind of text data, right? Although they can be structured to have different kind of information inside, like timestamp or have kind of template, but still they can be considered as a special type of text data. And the existing method usually, so for example, so that's the logs. They usually extract some kind of templates of those logs, and then map the log into those templates, so to form a sequence of events. So based on the sequence of events, they further do the analysis based on that for the anomaly detection, for other kind of debugging, or based on the sequence of events. So in this way, actually, after they transfer the text into one index, so that cannot lose a lot of information to help us to identify the real problem inside. Right? And also that can cause a lot of false anomalies, since for example, if you just change one word in the state, like for example, the state to status, so that's going to extract another template. So if you change the T3 to T5 here, so that's going to, normally that's going to detect an anomaly, but actually it doesn't exist, right? So by consider the semantic meaning of those words in the logs, that can help us to deal with those problems, and also can help us to transfer knowledge between different systems. Right. For example, we have different mail systems, but to extract the label is quite difficult for us to train the models. So if we have those different systems data that can be trained together, we can transfer the knowledge between different systems. So that can help us to deal with those real problems when we get into a new system, right? So that can efficiently help us to deal with the problem. So here we kind of treat the log analysis into document analysis. So we form those different logs in a time window. We treat them as one document, and then we further model them based on those documents. So that can help us to return those semantic meaning of those logs. This is one research still ongoing, but we can see some improvements based on our experiments. And another application is for the security. So in the security area, so actually we can see there are lots of documents and the reports. So that help us to describe the attacks into the system or the malware, how they behave, right? So we have different, larger amount of text data or documents or reports, and but for those documents, how to extract the useful information from that to help us to deal with the real problem. So that's also one very useful application. But it's also hard to directly apply the general NLP models to the specific domains. As we know that for example, for the entity recognition, we first need to specify the entity types, right? Then we train our model to extract those different entities. But in the security domain, the entity types are quite different from the open domain. So how to use as less as possible labels to help us to train the model. So that's really problems we encountered in the real world. So you know that if you have enough label, then everything going there will be no problem. But the truth is that it's very hard to obtain those labels. So here we also develop a distance supervised those methods to deal with the problem to help us to use nice label but train the model to get a similar level of performance. And after we get the entities and the relations of those reports, we want to formalize a cybersecurity knowledge graph. Then we know the behavior of those malware, like how the attack is conducted, and then if we get some new attack and we can match the behavior of the new attack to the knowledge graph, then that can help us to detect those new attacks. Right? So that's another application we have conducted in labs. Okay. Okay. So any questions after I introduce those models and the applications?
So I think we have a couple questions on the chat, and let me go back and read some of them. So one is a comment followed by a question. You appear to focus on how to predict the correct answer, but I always find that the most advancement comes from focusing on not being wrong. You mentioned penalizing a possible solution, but that's not quite the same as trying not to be wrong, which is most important for building user trust. And the question, could you modify your process to include an element of not being wrong?
Now I can see the trends. Okay. Most of the other ones comes from not being wrong. That's the solution, but that's quite the same as trying not to be wrong. Building with, I see. Okay. Not being wrong. Yeah, actually, not being wrong. So actually, that's quite important, right? If we provide any kind of output, so this quite a great question, direct to the point. So actually, in our learning process, we also have. So nowadays, most of the nonce function we include is to making the answer correct. But as you said, how to make the answer not wrong. So one actually in many models, I think there are some nonce function like the triplet nonce, right? They include one pair. So one is the positive, one is the correct answer, and the other one is the wrong answer, right? So in this way, we can also penalize those wrong answers. to make sure we do not get those wrong answers. So that's maybe one way that can solve your question here.
And then there's another question. The original BERT uses word piece, subword vocabulary. Do you use the same vocabulary? And what about the phrase pool? Is there a fixed token limit?
Okay. Vocabulary. Fixed token limit. Yeah, I think so. I think for the BERT, we use the same tool, like the tokenization. So I think maybe that's the same vocabulary you mentioned here. And for the phrase pool, we since fixed token limit, we just treat them as same as the word, how to tokenize the words in the phrases. So I think it's a similar process.
In your examples, they all English. Do your methods work on multiple languages?
Yeah, that's a good question. So actually for this model, we focus on one language, but actually in all labs, since we are a Japanese company, so actually we deal with a lot of those multi-language, like Japanese English too. And we have research focused on the cross-lingual learning to, for example, actually we have very limited source in Japanese for those labels. So how to learn from the English to help us to improve the performance in Japanese. So that's we have research work on this side.
That's very interesting. So again, Yanchi, thank you for giving the data science seminar this week. And I appreciate you spending the time with us and giving a very nice talk. Thank you very much.
Thank you for having me.